We're good. So, Carla, take it away. Present yourself and take it away.
Okay. I'm sorry. I want to start. Hello, everyone. I'm Carla Ràfols from Universitat Pompeu Fabra, and I will tell you about some work we've been doing with Alexandros Zakarakis, who's here, and with Nikitas, who's also here. And thank you, everyone, for showing up so early. Okay. So, Holography Accumulation, it's a fancy title. I realized that when I was preparing the slides that I was not using the word holography, so I will try to explain what's the title, so if I forget, tell me. Okay. Okay, so this talk I will give you some introduction to SNARKs and a motivation of the research problem we're trying to address here. And I will show how the ideas we have, very high level, how they apply to recursive proof and to privacy-preserving delegation of SNARK provers. So this will be, okay. So as you know, when we want to prove something with a SNARK, we have to represent computation in a certain way. Okay, so here a typical statement we might want to prove is circuit satisfiability. Here we have a small circuit, and we want to prove statements maybe of this kind. We want to show that the circuit evaluated on some certain public inputs, which are the X, results into some certain public output. This can be abstracted in a more general form into this R1CS rank 1 constraint system, which results in a system of this form where this dot stands for the Hadamard product. And I like to think of this kind of constraint system as proving three things at the same time. So it's proving that there have some public input relations, that there are some Hadamard product relations. So if you look at this circuit, in fact, what we are trying to prove is that there is a certain multiplicative relation between the left and the right outputs, inputs of the multiplication gate. So A are the left inputs, and B are the right inputs. And there is some set of linear relations that we want to prove. And for this talk, so for this talk, what I'm interested in highlighting is that these matrices, as you probably know, they are all sparse. They are big because they depend on the number of multiplicative gates, essentially, and some inputs. So here you have like the matrices that would result from this proof system. Okay, so they are sparse, but they are large. Okay. Okay. Okay, so if I do like that, it means change. Okay, so here you have an example, okay? And this generalized, sorry. Okay, so 2, please. 1 more. Okay, thank you. And this generalizes, like if you want to use more flexible constraint systems, because this allows you to reduce the size of the constraints, this generalizes to these customizable constraint systems, okay? As you may probably know, this comes from generalizing some way of writing constraints that appeared in the Plonk proof system. But it's essentially the same, okay? We want to prove these three things. Public input, Hadamard product, and linear relations. And the thing is that there's like as you probably know, when we want to write, want to prove things with a SNARK, we want to write all these linear relations as some kind of polynomial identities. And the interesting thing is that actually all these things we want to prove, like public input, can be done can be done by encoding every vector as a polynomial, and then you can see there's like a certain polynomial identity that maps public input, Hadamard product relation, and so on. But maybe you have no, like the only way we know how to prove linear relations is essentially we know how to prove one linear relation. We know how to prove an inner product relation in this polynomial identity. In fact, we want to prove like many linear relations, right? Like we want to prove that A Z is equal to the right output and so on. So how do we deal with this? Well, this is like a different way to classify proof systems and how do they deal with this problem, okay? You want to prove many linear relations, but in a non-interactive way, directly mapping these to polynomial identities, there's only, we only know how to prove one linear relation, which is one inner product. Okay, and then you can like think of systems like Plonk, hyperplonk, and so on. They are like permutation-based arguments. So in some sense, what they're doing is they don't prove R1CS, but they write the constraint system so that these matrices that appear that they have to prove are permutations. Okay, and then they use some identities between polynomials that, this is simplification, but essentially there is a way in which you can prove that something is a permutation. And then there's like another family of proof systems, which are Marlin, Fractal, Spartan. I'm basically talking about univariate polynomials, but like it's essentially the same for the multivariate case, okay? And these proof systems are link check based, okay? So what does it mean? So essentially when they want to prove like many linear relations, what they do is like they collapse, they get some random vector that comes from the verifier, and they collapse this set of linear relations to a single linear relation, okay? So we have this if and only if, where it's actually not an if and only if, this is with high probability, okay? So if the left side is true, if and only if this, so this becomes one inner product, and this is also an inner product of one vector, okay? So this is one vector in the row space of the matrix M. My point in this talk is that, well, there's a significant difference between these two different ways of proving linear relations. And one is that when you move to this kind of way of proving this permutation-based proofs, everything is private computation, okay? Why? Because if you want to prove, you're essentially proving that the two witnesses have a permutation of each other. So you need to know the witnesses. Whereas here, there is like a certain part of the computation that is public because you're proving two things, okay? So you first prove that the inner product relation is satisfied. And then you need to prove really that this vector, which is a vector in the row space of the matrix, is correctly defined. And this is something that actually the verifier could do himself because the matrix is public, it's part of the description of the circuit, but if it does it, then it's like the matrix is too big so that the verifier cannot really do that. Okay. So the main point of this talk is saying, okay, there are advantages for using this, for this way of proving constraints, both in recursive proof composition and in privacy-preserving delegation. So this is like maybe one of the main messages. There's like another message, but like, yeah, yeah, okay. So if we look at link chain-based argument, like we look at Marlin, for example, we have that we can divide it conceptually like something like this. In the first part, like there's a commitment to the witness, and then you get some challenges. And then in this outer sum check, you prove, you do some, you just send some terms that serve to prove all these polynomial identities that I said in the beginning, no? The public input, everything. Everything that is succinct. Then you get a challenge, and then there's like this part called the inner sum check, which is actually devoted to proving that this public computation is correct. Then there are like opening polynomials and so on. Okay, and actually the verifier predicate can be split in three parts. Okay, so there are like some succinct checks that the verifier needs to do, then it needs to check that the polynomials are correctly open, and then there is this orange predicate where the verifier is trying to show that this public computation is correct, okay? If you eliminate this is also a snark, but then it's like a snark with a linear verifier, because the verifier has to check this himself, okay? Next. Okay, so the point is that this part, okay, is relatively expensive, okay? This is something that's like, and this is like where I have to remember to explain the title of my talk, okay? This relates to like, this part can be avoided, but then you get like a linear verifier. It's not a pre-processing snark where the prover, where the verifier can check everything succinctly. Okay, so it's like related to, this part is related to having this thing called holography, like, okay, a certain way of pre-processing the computation so that everything can be succinct. It's significant because the cost of this thing is essentially in a large, I didn't mean to say O of k MSMs. I mean to say it costs something like a linear number of group operations in K, where K is the sparsity of these matrices, okay? It's the maximum size of these matrices, which in reality, it's a small constant. Probably it's 1.5, 2, and 3, but it's still a good portion, okay? And then it also means K log K field operations. Asymptotically, if you look at the cost of this, it's not fixed, right? Because it depends on the matrix. It's not like a fixed portion of the total computation. And like if you look at Marlin, even like how you prove later that this thing is correct means you have to have like a large degree SRS, okay? It's something 6 times K or something like that. Okay. And I want to say that, I want to say that this overhead, if you look at things like Fractal, which is like some essentially Aurora, like is a hash-based proof system, which is essentially like Aurora, where you put like a succinct verifier. You can see in their experiments, this part is, this public computation part is not negligible. Okay, so how do we apply this to recursive proof composition? So let's think of incrementally verifiable computation that I'm sure almost everyone in this audience has heard about before. So essentially, we have like a computation, and we're dividing it into small, we're doing it incrementally, so we're doing like one chunk at a time, okay? And then it's like at each step, it's like a non-deterministic computation. There's like a certain input and so on. So in each step, we want to make sure that some certain relation, some function of Zi is equal to the next evaluation. So the way people introduce verifiable computation, the idea was like, okay, so what we will do in each step is like prove that the computation is correct, so that the function f really is evaluated correctly, and also give a proof of a proof that the proof of the previous computation verifies. Okay, so when we have like a prover, it basically has 2 parts. Okay, on one hand, the prover, this is the prover that is executing each of the steps, is trying to first check that the function is correct, and then it will prove that this circuit, which is the verifier of the snark, okay, evaluates to 1, so that the proof verifies. And then there's been like a series of works, starting by Halo, then formalizing this accumulation notion and folding and so on, where the idea is, okay, like the problem is that this prover becomes really expensive because like the snark prover is not cheap in the first place, and then you're putting inside the verifier, which means like you have to arithmetize you have to create a circuit that represents the verifier, and this grows like quickly and very much when, because of the type of operations you're doing with the verifier, okay? So there was this idea, okay, what if some part of the computation is deferred, okay? So what if the prover doesn't execute the full computation, but keeps some part for the end, and at each step, the sum of the computation is accumulated, okay? So it means like you have to prove a certain relation inside here, so the idea is instead of proving it, you just batch all the statements you want to prove at each of the steps, okay? So essentially it's something like that, okay? In each step, the name folding is a bit confused because it's used in different ways, but essentially the idea is, okay, there is a part of the computation that we don't want to do, we just want to batch it together with similar computations, okay? In a way that, which has like these properties. So if the final computation, if the final statement is true, then the other statements are also true, okay? So the claims are accumulated into one final claim. Okay, and so what is the state of the art? So that people have applied this idea to build IBC in different ways and contexts. So first we had like this idea of full recursion, where like all the computation is executed at every step, the verifier, like the full proof is checked at every step, and so on. Then there was this notion of atomic accumulation, which the proof is completely computed, so the prover is fully executed, but some part of the polynomial opening is not fully checked. And then finally, we have this notion of folding and split accumulation, which what it's doing is like pushing this approach to the limit. No? So it's like essentially the verifier doesn't check anything, it just checks that these checks are accumulated correctly, okay? So that all the computation that is deferred is like correctly compressed to a new step of computation. Yes, and, okay, so next. So we have something like that, okay? So for this type of snark, the yellow part is what is executed. So everything is executed, everything is checked. Here, everything is executed, but there is a certain part that is actually also public that is not verified. And here, we have that only this part is executed, okay? And all you verify is that the computation is collapsed correctly. So, one important difference between these two and these two approaches is that here, actually, there is some private state that needs to be passed to the rest of the computation, right? Because you are essentially not proving anything, and at some point you will need to prove things, and at the moment where you need to prove things, you will need to be able to know the witness. Okay, so our point, like this is what we do in our paper that I hope to put in preprint next week, is to revisit this an approach introduced by Darling, actually in some ZK proof, where what they suggested is like this part, this orange predicate that checks that the public computation is correct, is not, I have 6, okay, is not fully executed. Okay, and so it's essentially what is the prover that it executed is everything except this part. Okay, and then this predicate is like deferred to the fact proving this predicate is deferred to the end. Okay. Sorry, I forgot. I want to say that this is also like here there's also no private state that is passed to the next computation. Okay. Next, please. Okay, so that's our results that we will put on preprint. So we revisit this proof system. We make it slightly more efficient and show how to generate to multiple state. And I think here, like the point I want to make is that and I think that's the really important point, is that I see no reason why you should ever use full recursion, okay? So like, so full recursion is like slightly, like this is also like a relatively expensive approach because most things are checked, but yeah. Okay, but anyway, like that's the point of the, I'm trying to be fast now and it's going too fast, okay? So that's one of the main takeaways, okay? Like, don't use full recursion, use this type of accumulation. And finally, we have other results like showing that how to prove this part of the computation independently of the sparsity of the matrix using inner pairing products equation. Okay, so last, I have 5 minutes, no, 4, 3. Okay, my timer doesn't see. Okay, so the second application is to privacy preserving delegation of computation. In general, there's like several works that are trying to do this now. And like what we want is to, computing as NARC is relatively expensive, so like we can think of delegating this to a set of provers. Why? Well, because the person delegated, the user, doesn't want to give the full witness to everyone. So like with the research question is like, okay, can we think of amortizing some of the work, given that this, like, assuming there is like a server that is doing computation for many people. Okay, so please. So, and then because of this, we again focus on this Marlin proof system where we remove this part, like the linear check, the link check, we split it in two, so we don't prove this part. Okay? And that's actually the witness-dependent computation part. The rest is witness-independent. So intuitively, we can think a scenario where this part is executed locally, and the public part is delegated to some computation server that executes these proofs. And the thing is that actually that's very convenient to delegate, because there's like, this is like a constant size string. So anybody can do that, but this server just like, it's relatively expensive. This server can do this for you. And then later you just can check a full proof, but verifying these two parts of the proof independently. And the idea that we propose is to amortize this public computation. There's a server that is doing it for many people. How can you amortize it? And then we think of this orange server that's doing all this public computation as something like this. So now you can move 5 slides, please. Okay, so it's getting statements from many people. It accumulates, it sort of like folds and aggregates all these statements into a single one that he sends to the parties. And then it just proves this one single statement. Okay, this would be an idea. So what is missing in this approach? Well, the users, they need to receive a proof that the final aggregated statements included their own statements, okay? Otherwise, they will think, they know the proof that the last statement is true, but they don't know that their particular statement is included in the proof, okay? So they all get, like, we can think that they all get a proof that their statement was included in the final proof. What's the problem? That if you do apply this solution naively, then each of the provers will know everyone else's statements. That's something we don't want, like, okay, because it doesn't make sense in this scenario. So what's the solution? So the solution is based on a paper we had like with Alexandros years ago, which is folding scheme with local verification. Okay, we have several users. We build a tree, so we aggregate all their statements. And the nice thing is that actually you can verify. It's like a Merkle tree sort of approach. Okay, you can verify that your statement was included in the final aggregated statement in a sublinear way by just getting a path of aggregated statements. So this is the final slide. So what do we achieve with this approach? We have like a trade-off between the cost server who's trying to compute on the proofs and the complexity of the verifier, right? Like each of the individual verifiers will pay some little extra cost, so which is this. So each verifier will check that the private computation was correct. It will check that this final aggregated statement is proven correctly. And then it will have this small proof, which is the small proof that says that his statement, it was correctly included in the final statement that you want to prove. Sorry, I will put the time. Too many technical problems. Okay, and that's it.
Big applause for Carla. Thank you, Carla. And sorry for the small rush there. Do we have any questions?
So in the delegation idea is really nice. I didn't. Can you repeat? I didn't understand exactly what is the work that's left for the client to do. It seems like it's still not constant.
No, it's not constant. But like the point is that it's two different things. Okay, there is like this witness-dependent computation, and this part is the part that you should delegate. So either
Witness
compute
independent. Witness
Sorry?
independent. Witness independent. You delegate.
No, so you delegate the witness-independent part, and this is amortized. And then there is the other part.
Right.
It's not constant. It's cheap. It's like something like dominated by 5 MSMs, like witness.
Yeah.
And this, like the point is that this you can distribute independently. Mm-hmm. So I mean, actually, that's a good point. Like you had this paper with
Alex
Ozdemir, no?
Yeah.
And you investigated how efficient was it to do MPC for computing these NARCs, and like one of the conclusions was that Marlin was more MPC friendly, and this confirms these results, but also says like I guess that really the computation that you need to do Windows independently is like minimal.
I see. So the MPC really only have to be applied to a small part of
Yes.
the computation, not all of it.
Which I guess like people do it indirectly because maybe they already take these into account, but like I think like with this approach, the total cost proof is something like when you divide it by the number of proofs is something like 5 MSMs in total.
Yeah, very cool. Got it. Thank you.
Thank you. I actually remember when Dan spoke about accumulation schemes in a previous older ZK proof. So it's good to see that the idea continues. Thank you again, Carla. We're now gonna hear from Michael Adjej on optimized ZK proofs for Pali-based 2PC ECDSA. Thank you, Carla. You can give it to Michael straight. I just want to apologize for the kind of pressure at the last minute. I know that the schedule says 30 minutes, but that includes like